All right. Let's get ready to dive deep into this fascinating world where math and programming come together. We're going to be exploring um, this excerpt from an article that you sent in. It's titled "The Connection Between Math and Programming: Unlocking the Power of Algorithmic Thinking."
I love that title, by the way. It's like we're about to discover the secret code behind the code, We'll be seeing how math is like the engine that's actually driving the digital world we live in.
Yeah. And what's really cool about all this, it's not just for, like hardcore software engineers or anything like that. Even if you're just starting out with coding, getting a handle on these connections can really make you a much more intuitive and effective programmer for sure.
So let's break this down a bit. The article jumps right into how both math and programming are all about problem solving, right?
Yeah.
They both involve taking these big complex challenges and
Finally.
breaking them down into smaller steps,
Yeah.
more manageable steps, right? Kind of like a puzzle. Exactly. It's all about that structured, logical thinking process. Kind of like when you're building with Legos, right? You need to follow the instructions step by step to create something awesome. And math and programming demand that same kind of precision.
Totally. Now, the article also talks about abstraction being a key connection here. I know that might sound kind of intimidating to some people, but it's actually a really powerful idea. So can you help us understand what abstraction actually means in both math and programming? How would you explain that?
Sure. So in math, you can think of abstraction like creating a blueprint. It's basically a general formula that can actually represent a whole bunch of specific equations. And guess what? We actually do the same thing in programming.
Oh, okay. I think I see where you're going with this. Is it kind of like when we use object-oriented programming, when we create those reusable blueprints that we call classes?
You got it. Yeah, those classes are basically abstract concepts that let us create specific instances or objects that are based on that blueprint. It's like having a cookie cutter.
Hmm.
You can use it to make a bunch of different cookies, but that shape, the shape always stays the same. And this makes our code way more organized, adaptable, and much easier to work with in the long run.
Okay, yeah, I'm starting to see how these like mathematical principles are kind of baked right into the way that we write code. And speaking of baking, right, both math and programming, they require a lot of precision. Like even one tiny error can really throw everything off.
Yeah, you hit the nail on the head there. Like a misplaced decimal in a calculation can lead to a totally wonky result, right? Just like a missing semicolon can make your code crash. Attention to detail is super crucial in both worlds.
Makes total sense. Now, the article highlights a few specific math concepts that we might not realize we actually use every day in programming. So let's start with algebra. How does that fit into the coding world?
Okay, so think about variables in your code. They're basically like those X's and Y's that we used in algebra class, right? When you assign a value to a variable in your code, and then you manipulate it with different operations, you're doing algebra. And understanding those algebraic expressions can really help you see the relationships between those variables. And this can make your code much more efficient.
I see. And the article even gives this like specific example of using code to calculate the average of a list of numbers, right? Which seems deceptively simple when you look at the code, but underneath, it's pure algebra.
Right, you're summing up values, you're dividing by the count. It's all those same algebraic principles at work. And this type of thinking really applies to even more complex algorithms for sure. The better you understand algebra, the easier it is to kind of translate those concepts into elegant and efficient code.
I like that. Elegant and efficient code. Now, this is where it gets really interesting, I think. Geometry. It's not the first thing that comes to mind when we think about coding, right? But it actually plays a huge role in things like game development and data visualization.
Absolutely. When you are creating and manipulating 3D objects in a game, or even visualizing data in a graph, you're essentially using geometry, straight up. The article mentions the Pythagorean theorem, which, we all learned in school, right? Well, guess what? It's used all the time in game development to calculate distances between different points.
Oh, wow. And they even provide the actual code for that distance calculation in the article. It's really cool to see, like, the Pythagorean theorem come to life in code form. You know what I mean?
Okay, but what about calculus? That's a subject that I think makes some people sweat a little bit, but it has a massive impact on specific areas of programming, right?
You bet. When we start getting into optimization problems and machine learning, especially neural networks, calculus becomes absolutely essential. Concepts like derivatives and gradients are really at the heart of those powerful algorithms. The article uses the example of gradient descent, which is really interesting. It's all about finding the minimum value of a function, kind of like finding the lowest point in a valley. So it's like calculus helps us create algorithms that can learn and adapt, which is pretty amazing when you think about it. I'm realizing now that math really is like the secret language behind so much of what we do in programming.
Exactly. It provides that underlying layer of logic and structure that makes everything work. But there's another area of math that's super important, and that's discrete mathematics. This branch of math focuses on distinct values, things like integers and graphs and sets. All of these are super crucial for designing algorithms and data structures.
Okay, the article uses graph theory as an example. I'm guessing that's relevant for things like social networks and maybe mapping apps, right? Things like that.
Spot on. Yeah, graph theory helps us model all these relationships and connections, which are really essential for, like, optimizing routes
Hmm.
or analyzing networks and so much more. And the article even provides code examples for how to represent a graph using data structures. It's so cool how these, like, abstract mathematical concepts become tangible when you actually see them in code.
Yeah. Wow, we've really covered a lot of ground here, from algebra and geometry to calculus and discrete math. But how does all this math knowledge actually translate into creating those clever algorithms? The ones that power our digital world. That's where things get really exciting, don't you think?
Oh, yeah, you're absolutely right. And that's exactly where we'll pick up next time. We'll be exploring how all this math-powered thinking actually influences the design of these
Mm.
elegant and efficient algorithms that make everything work.
Awesome. Can't wait. I already feel like I'm seeing programming in a whole new light. To all our listeners, stay tuned for part 2, where we're going to be diving even deeper into this world of algorithms and really see how math is the magic behind their power.
It could be good.
It is going to be good. Welcome back. So, last time, we uncovered how all these fundamental math concepts, algebra, geometry, calculus, discrete math, how all those are kind of woven into the fabric of programming itself. So now, let's kind of shift gears a little bit and see how all of this math-powered thinking actually helps us design these clever algorithms that make our digital world tick.
It's really cool, right? Because, you know, we're not just searching for any old solution when we talk about designing algorithms. We're really on a quest to find, like, the best possible solution. And that's really where math shines, I think. It gives us the tools that we need to analyze and optimize how efficient our code actually is.
Yeah, and the article talks about time and space complexity, which sounds a little technical. I'm guessing this is all about understanding how our algorithms perform in the real world, how they actually work when they're put to the test, right?
Absolutely. Like, imagine you have two different ways to sort a list of names, right? One method might take forever if you have a really long list, but the other one is super speedy. So time complexity helps us analyze how that runtime of an algorithm actually changes as the input size grows.
So it's like comparing how much longer it takes to sort a list of 10 names versus a list of 10,000 names, using those two different methods, right?
Exactly. And to express this mathematically, we use something called big O notation. You ever heard of that?
I've heard of it, but honestly, I don't fully understand it. Can you break it down for me?
Yeah, for sure. It's basically a way to describe how quickly an algorithm's time or space requirements increase
Yeah.
as that input gets larger and larger. It's kind of like shorthand for just describing an algorithm's efficiency.
Okay, I think I'm starting to get it. Can you give us an example of how this big O notation actually works in practice?
Yeah, the article uses this really great example. Linear search versus binary search. So imagine you're looking for a specific word in a dictionary. Linear search would be like flipping through every single page, one by one, until you finally found the word you were looking for. But a binary search, on the other hand, that's way smarter. You would open the dictionary in the middle, see if that word is before or after that point, and then just keep having that search space until you find your word.
So binary search is kind of like playing that higher or lower guessing game, right? You keep narrowing down the possibilities until you get to the answer.
Exactly. And that's where, like, the elegance of big O notation really comes in. So, like, a linear search has a time complexity of O of n, which means that the time it takes actually increases proportionally to the number of items in your list. But a binary search, with that, like, clever halving strategy, has a time complexity of O of log n. And this means that it actually grows much more slowly as that input size increases.
Okay, so even though both of those algorithms get to the same goal, they both find that specific item in the end. One is way more efficient than the other. And big O notation just gives us a way to express that difference mathematically, right?
Absolutely. It's a really powerful tool for comparing and choosing the best algorithm for a specific task, especially when you're working with massive data sets.
Yeah, I can imagine that's super important in the real world. Now, the article also talks about recursion, where a function basically calls itself, which I always found a bit confusing. But I have a feeling that there's kind of a mathematical connection there too, right?
You're right on the money. Yeah, recursion is very closely tied to the mathematical concept of induction. Both of those really involve breaking down a problem into these smaller, like self-similar subproblems. It's kind of like those Russian nesting dolls, where each one contains like a smaller version of itself. And recursion works in that same way. It solves a problem by calling itself to solve these smaller instances of that same problem.
Okay, I think I'm starting to see it. The article gives the example of calculating the factorial of a number, which is like a classic recursive problem, right?
Yeah,
Can you walk us through that?
sure. So like the factorial of a number is basically just the product of all the positive integers
Yeah.
that are less than or equal to that number. Like the factorial of 5, you write that as 5 with an exclamation point, is 5 times 4 times 3 times 2 times 1, which equals 120. Now you can calculate this recursively by defining that factorial of n as n multiplied by the factorial of n minus 1. So 5 factorial is 5 times 4 factorial, and then 4 factorial is 4 times 3 factorial, and so on until you get to 1 factorial, which is just 1.
Okay, so it's like breaking down this big calculation
Yeah.
into a series of smaller ones. And each smaller one kind of depends on the result of the one before it, right? And this recursive pattern, it shows up in all sorts of programming problems, doesn't it?
Oh yeah, absolutely. Another classic example is the Fibonacci sequence, where each number is basically the sum of the two preceding ones. And you can actually define that recursively. Like the nth Fibonacci number is the sum of the n minus 1th and the n minus 12th Fibonacci numbers. So that recursive definition makes it really easy to code up a function to calculate, any Fibonacci number you want.
So recursion isn't just some weird programming trick then. It's actually rooted in this kind of fundamental mathematical concept of breaking down problems into these smaller, self-similar pieces. Okay, that makes it a lot less intimidating now. So we've talked about efficiency and recursion, but real-world programming is often about tackling these really messy, complex problems, right? Where the best solution isn't always obvious right away. And the article mentions optimization problems. Is that kind of what they're referring to there?
Exactly. Think about like everyday situations, right? Like planning the most efficient route for deliveries or figuring out how to allocate resources in a project or even just packing a suitcase for a trip. All of these are optimization problems. We're trying to find like the best solution among a huge number of possibilities.
Yeah, and I'm guessing math kind of provides us with the tools to tackle these types of challenges, right?
Oh yeah, for sure. Math is like our optimization toolkit, basically. We have things like linear programming
Yeah.
and dynamic programming and a whole bunch of other algorithms that all stem from these mathematical principles. And these techniques really help us like systematically model these problems, taking into account any constraints and objectives that we have.
The article mentions the knapsack problem as an example. Can you give us a quick overview of what that is?
So imagine you're going on a camping trip and you have a knapsack that has, limited weight capacity. You also have all this stuff you want to bring. But, each item has its own weight and its own value, right? The knapsack problem is all about figuring out which items to pack to maximize the total value that you're carrying in your knapsack without going over that weight limit.
So it's like a real-life optimization puzzle, basically. And there are mathematical algorithms that can actually help us solve this.
You bet. Dynamic programming is a really cool technique that we use a lot for the knapsack problem. It basically breaks that problem down into smaller overlapping subproblems. And then it kind of builds up the solution step by step. It's like figuring out the optimal packing strategy by considering each item one by one and just making the best decision at each step along the way.
Okay, this is all really starting to come together now. We've gone from these like basic mathematical concepts to seeing how they really empower us to design and analyze and optimize these algorithms for all sorts of real-world problems that we encounter all the time. It's like math gives us the blueprint for how to build these elegant and efficient solutions.
Exactly. And you know what? We've only scratched the surface. There are so many specialized areas where this fusion of math and programming is really pushing the boundaries of what's possible.
Okay, I can't wait to dive into those. I'm really eager to see how this whole math programming connection plays out in specific fields like cryptography, game development, and machine learning.
And that's exactly where we're headed next time. Get ready for a wild ride as we explore how math is kind of like the secret sauce behind some of the most exciting and impactful technologies that are shaping our world.
Awesome. This is already blowing my mind. It's like a whole new dimension of programming has been unlocked. Until next time, everybody, keep those mental gears turning. All right, welcome back. We've journeyed through the core concepts of math in programming. We've seen how they fuel the creation of those, efficient algorithms and all that. But now, buckle up, because we're going to zoom into specific tech fields
Yeah.
where this math programming synergy really takes center
You
stage.
get ready for liftoff.
Yeah.
Yeah, it's mind-blowing how math acts as this like hidden engine in so many different areas of technology. So let's start with a field that's both mysterious and absolutely crucial for our digital lives, cryptography.
Okay, cryptography, the art of keeping our online secrets safe, right? But where does math actually fit into all this? Like this world of encryption and decryption.
Oh, it's fundamental.
All right.
It's literally the foundation, the bedrock upon which all of cryptography is built. Number theory especially, the study of prime numbers
Mm.
and how they behave, that plays a starring role.
Yeah.
Think about the RSA algorithm, which is used everywhere to secure online transactions. It's actually based on a really interesting mathematical challenge.
Okay, what's that?
It's all about the difficulty of factoring large numbers. Turns out that even with super powerful computers, it's incredibly hard to take a really big number and break it down into its prime factors. It's like trying to figure out the exact combination of ingredients. That went into this like super complex dish, right? Like nearly impossible to do without the recipe.
So it's like creating this incredibly strong lock that's almost impossible to pick without the right key. And that key is basically like based on these mathematical principles.
Precisely. And the article even gives us a little sneak peek into this world with a code snippet that demonstrates modular exponentiation, which is a core concept in cryptography. It's like a little taste of the math that's working tirelessly behind the scenes to protect our online transactions and keep our data confidential.
That's amazing. It's incredible to think about all this complex math that's happening every time we make an online purchase or send a secure message. Okay, let's shift gears to something a little more visual, game development. I know there's a lot of math involved in creating those immersive 3D worlds that we all love, right? Can you break down some of the specifics for us?
Sure. So imagine you're designing a character, right? That's moving through this virtual environment. Every step they take, every turn they make, every interaction with the objects in that world. It's all governed by these mathematical calculations. Linear algebra and trigonometry are kind of the stars of the show here.
Yeah, and the article uses that example of rotating a 2D point. And it's interesting because even that, that seemingly simple action requires these trigonometric functions like sine and cosine to calculate the new coordinates after that rotation.
Exactly. And this applies to so many things in game development. Like think about simulating realistic lighting or collisions between objects. Even the physics of how clothing or hair moves. It's all grounded in these mathematical models and algorithms.
Wow, so are you saying that game developers need to be like math whizzes to
Yeah.
bring these virtual worlds to life?
Well, having a solid grasp of math is definitely a huge advantage for sure. It allows those game developers to really understand how to manipulate objects in 3D space, create really realistic physics, and ultimately just build those visually stunning and immersive experiences that we
Oh.
all enjoy.
It's incredible how much is going on behind the scenes of our favorite games. Okay, let's move on to our final destination. A field that's been making waves everywhere. Data science and machine learning. We all know that statistics is involved, obviously. But what other math concepts are kind of at play here?
Right. Well, statistics is definitely fundamental to the whole thing. It gives us those tools to analyze data, find patterns, and make predictions. But linear algebra is also crucial, especially when you're working with, massive data sets and you're performing those complex matrix operations that are used to train all these machine learning models.
Yeah, the article actually gives a code example for linear regression, which I'm guessing is a pretty key technique in machine learning, right?
It is. Linear regression is used to model the relationship between variables so that we can make predictions about future outcomes. And the code snippet shows how gradient descent, which is that optimization algorithm from calculus, is used to find the line that best fits a set of data points. It's kind of like finding that trend line that best represents a pattern in your data.
It's fascinating how all these different mathematical concepts come together to create these really powerful tools for analyzing data and extracting these meaningful insights.
And we're only just scratching the surface. I mean, machine learning relies on such a vast array of sophisticated mathematical techniques, from probability and calculus to optimization and linear algebra. It's a field where that combination of math and programming is constantly pushing the boundaries of what's possible.
So after this whirlwind tour through the world of math and programming, What's the main takeaway for our listeners? What do you hope they'll walk away with today?
I really hope they see that math isn't just some academic subject that's confined to textbooks. It's really the hidden language, the driving force behind the code, the algorithms, and ultimately the technologies that shape our world, right? So whether you're
Yeah.
passionate about building really secure systems
Yes.
or designing incredible games or unlocking those secrets hidden within data, math is this incredibly powerful tool.
I love that. And the article provides some, really great advice for anyone who wants to boost their math skills for programming, practicing problem solving, diving deeper into algorithms and data structures, exploring discrete math, linear algebra, and statistics. It's all about building that solid mathematical foundation.
And the best part is, even if you weren't, someone who loved math in school, there are so many amazing resources and online tools available today that make learning really fun and engaging. You can find courses, you can find interactive tutorials. There are even games that can help you grasp these concepts in a way that really makes sense to you.
So, to all our listeners out there, remember, embrace the power of math, unlock those secrets of code, and who knows what incredible things you might create. As we've seen in this deep dive, the fusion of math and programming really has the power to transform our world, and there are endless possibilities waiting to be discovered by those who dare to explore this amazing intersection. Thanks for joining us.
It's been a pleasure.